I am going to go ahead and share my screen. And hopefully you all receive the slides from Josh. And if you all have questions, if you could please send it to the questions for Jameelah person in the chat. That's my other screen that's up. And we're gonna go ahead and get started. And if there's some echo that you guys still hear, just let me know. So my name is Jameelah. As you all know, today we're covering spectroscopy and organic chemistry lab techniques. Nice to meet you all too. Thank you. I'm very excited for teaching today. So spectroscopy provides structural information about any molecule. The key is to use all spec data to identify the molecule in the end. I know you all covered a few things with Todd, so some things we're going to go over briefly, and then some things we'll go over in more detail. The first thing we will cover is UV, so that's ultraviolet visible light, or UV. The purpose of UV is a quantitative measure of how much light is absorbed by a chemical substance in which that light passes through. So your visible light range will be from 200 to 800 nanometers. This wavelength is obtained in a vacuum for accuracy. That's how brilliant scientists came up with that value, if you were wondering. UV is used to analyze pi bonds, especially in conjugated systems. So the key absorbances for MCAT purposes. So I'll go through a few things here and then we'll go over those absorbances. When light gets absorbed, it causes electrons to jump from low energy to an excited state. So you're going from bonding to pi star bonding, which is bonding to anti-bonding transition, which we'll look at in this slide after. So our gamma max changes with the amount of conjugation within that molecule. So electrons move from ground state to excited state when light is absorbed, and that's called the excitation by light. So as light comes into the molecule and it is absorbed, then the electrons jump from ground state into their excited state. I'm hoping that I can see everybody's chats here. LUMO is the anti-bonding orbital. Okay, just give me 1 second. So the anti-bonding will be when the electron jumps from Yes, so yes, you're right. So you're going to go from the highest occupied molecular orbital into the lowest occupied molecular orbital. So on the left, you'll see the bonding, pi bonding, and then on the right, you'll see the anti-bonding. So that's pi star. Does that answer your question? Yes, okay. Thank you very much. And I'm sorry if I keep repeating myself, I keep hearing this echo, so it's kind of distracting. As conjugation increases, the wavelength, which is gamma max, also increases. As conjugation is added into a molecule, absorbance shifts into the visible range. So the more conjugation you have, the more colorful your molecule will be. Just a fun fact there. On the MCAT, you may have to calculate the index of unsaturation of the molecule. So be able to calculate this no matter what format the molecule is given in. Does that make sense? So you're going to be multiplying 2 times the carbon plus the number of nitrogens in your molecule minus the hydrogens in your molecule minus the halogens. You're going to add 2 and then divide by 2. And the units of unsaturation reveal the number of pi bonds and rings in an organic molecule. Yeah, that's a great comment, Tiffany. Todd does a really great job of giving great examples to remember. I don't have one, but I'll definitely ask Todd for his because I know his is good. Everybody got that one? So IHD stands for the index of hydrogen deficiency. So saturated versus unsaturated, the best example that I can give you all for this one is butter versus olive oil. So which one of these, as a quick review, do you all think is a saturated molecule? And which one do you think is an unsaturated molecule? The right is saturated. Okay, left is unsaturated. That is correct. So your unsaturated, this will come in handy as well in biochemistry. So your unsaturated fatty acids will always have pi bonds, okay? The more pi bonds you have, the more unsaturated your molecule is. Saturated means saturated in hydrogens. So if your molecule is saturated, it has to be saturated in hydrogens. That's how I was able to remember that. So good job on that, everybody. So here is a sample UV spec. So on the left, you can see that the absorbance is unitless and it ranges from 0 to 1. And on the bottom, you'll see that the wavelength is usually given with, the wavelength is measured in nanometers. Sorry about that. Let's see, somebody's asking a question. Would butter be the saturated molecule? So your fatty acids are going to be more fluid than butter. So your butter is going to be saturated. That's correct. Okay. Okay, let's continue with this sample UV spec. This information tells you that the molecule of interest is colorless because it is outside of the visible light range and probably has fewer degrees of unsaturation compared to other molecules. But the key is to combine other data with UV for successful structure elucidation. So all of these, all spec scientists will use together to really pinpoint what molecule they have. Let's see. And on here, your gamma max is going to be 222 nanometers. And UV spec takes the max absorbance point as gamma max, in case you're confused about that, which I don't think you all will be. So our sample UV spec one more time. So our gamma max for this, the molecule on the left is 187 nanometers. And as you can see from left to right, the wavelength is increasing. So you also know from previous slide that as the conjugation or pi bonds increase in the molecule, so does the wavelength. So can you all do a calculation for IHD for each of these molecules so we can see what we get? And I will give you all a few minutes to do that. No, oxygen is not part of the equation, not for IHD. IHD, sorry about that. No problem. And so someone asks, the UV range is from 200 to 800 nanometers, but visible light is only from 400 to 700. Yes, that's correct. Our human eye can only see a certain range on that um, of visible light. And I'll try to find an example for you all for that one. Okay, I'm gonna wait for a few more answers to come in, and then we'll keep moving through the slides. Okay, so we will go forward now. Hopefully everybody had a chance to answer those. So our equation, back to our IHD equation. Why do I keep saying G? It is, you're going to multiply 2 times the number of carbons plus the number of nitrogens minus the number of hydrogens in your molecule minus any halogens plus 2, and then divide that all by 2. So if we look at these, Let me see if I can write on here. Oh, I can. Interesting. Okay. Fun fact. So for the first one, we have 3 carbons. So we multiply 2 times 3 plus 2 minus 6 divided by 2, and we get 1. So we should see 1 pi bond present in the molecule of interest for number 1, and we do. It's right here. Okay. When you get good at these, you'll be able to just point it out without actually doing the calculation. So for number 2, we have 2 times 4 carbons plus 2 minus 6 divided by 2. That gives you 2 pi bonds in the molecule of interest. Let's double check, and that's 1 and 2. In the third one, if you want to guess before we do the calculation, you have 3 there. All right. So we have 3 pi bonds on the molecule of interest. Does anybody have any questions on this? Yes, so I do have some slides specifically dedicated to that. Yes, so I will definitely do that. I don't mind. So we will be moving on to infrared, which is IR. IR is special because every organic molecule produces a unique IR spectrum. I really loved IR when I was taking organic chemistry. So the purpose of IR is the measurement of electromagnetic radiation absorbed by the molecule of interest. So at 1700 centimeters, you will see IR, a carbonyl group. So IR is used to determine the functional group present in your molecule of interest. So when you know these, when you know these key absorbances, you'll be able to pick out those functional groups very quickly. So the centimeters to the -1 is called a wave number. The range of these absorbances for IR range from 4,000 to 600. The graph you will see is a recording of light absorbed per transmission as a function of the wave number. Each type of bond reveals a specific frequency at which light is absorbed. And here are the key absorbances that you will need to know for sure for your MCAT. So the ranges you'll see here are 4,000. The wave numbers are going to go from 4,000 to 1,300. And that's the functional group region. There's also a part called the fingerprint region, but we can't really read any functional group using the fingerprint region, if you remember from your organic chemistry classes. So this is one point that someone just asked me for specific MCAT pertinent things. So for IR spec on the MCAT, the graphs will not always be given every time, which is why knowing your key absorbances will take you farther. So these key absorbances, if you have those locked in your mind, you'll know, what molecule you'll have, and you'll be able to recover it more quickly than trying to memorize a graph. So you are likely to be asked what functional group exists in this molecule. So they might give you, I'll give you an example after this slide, but they'll ask you what functional group exists in this molecule. And then you will be given 4 different answer choices. If you only see one functional group in the molecule, You should choose the answer that only gives one absorbance. Does that make sense? Okay. Here's an example. What functional group is likely to be found in the molecule of interest, given IR absorbance value 1700? So there's 4 different answer choices here. You have aldehyde, ketone, cyclic ether, or all the above have an absorbance between 1700 and 1750. This is kind of a trick question within a question. So I will wait and see if anyone answers this one. Then we'll keep going. So remember when I said they're not always going to give you a graph or a photograph or a graph of the picture? This is one of those questions. Okay. So the aldehyde has an absorbance between 1740 and 1720. We're going to go over that now. Yes, we're going to go over that now. The answer is not D. So yeah, the answer is B. So the aldehyde has an absorbance between 1740 and 1720. So we know that that's too high because the absorbance given here was 1700. So we're looking for an absorbance close to 1700. Yeah, it was a trick question for sure, especially that last one, because I gave you 2 absorbances. And then I gave you 1700 as the given. So cyclic ether lies between 1300 and 1000, and that's way too low for 1700, which was given to us. All of the above. So the statement may be true, but you are given 1700 only. So we're only looking for one absorbance peak that exists in the molecule of interest, and that would be that ketone that we saw. Okay. Yeah, the aldehyde is tricky. So let's go on to proton NMR. So that's nuclear magnetic resonance. Proton NMR. So in organic chemistry, we learned that we have carbon NMR spec and we have proton NMR spec. I have never seen carbon NMR on the MCAT, but that's just my experience. So yes, I would suggest, can you repeat your tip? Yes, I can. I'll do that. So I would suggest memorizing a few IR spec data. So these absorbances, I would definitely put some of those in your head. I would say this one's super easy because it's very obvious. Alcohol is the most obvious absorbance, in my opinion, because of how broad it is. And sometimes the amines can be tricky, so I would look into those. But definitely that carbonyl and then the alcohol and the carbon bonded to the H, which is at 13,000. About the single functional group. Yes, I can repeat that. So here's the exam tip. So on the exam, they might give you a molecule and they might ask you, what functional group exists within this molecule? Okay. They'll give you an A, B, C, or D. Within your A, B, C, or D, they might put like, let's see. Oh, didn't we do that? They might put, oh no, that's the wrong one. Okay. In your A, B, C, or D, they might give you 1700. They might give you 3000. They might give you, I'm just making stuff up now. And they might give you, This is kind of messy, but hopefully it gets the point across. Okay. So in the answer choices, you see that there's only one answer choice with one functional group. With one absorbance. So what functional group exists in this molecule? So if you have these in your head already, you know that this is a ketone, A is a ketone. Yes, exactly. What functional group exists in this molecule? So they might list the names like I listed them here in your answer choices, or they might switch it. So they might give you these up here, or they might give you the wave numbers down here, and then ask for you to figure out which one is which. So basically the exam tip was, if you know that your molecule has one functional group and one key absorbance, then that's the obvious answer. Does that make sense? If you only see one functional group in the molecule, you should choose the answer that only gives one absorbance. Okay, thank you very much. I'm glad that was able to become more clear for you. Okay, let's keep moving. I'll come back to questions in just a second. Okay, so NMR is a measure of magnetic spin associated with the hydrogen nucleus, also called HNMR. So, like I said before, in organic chemistry, most of you have probably gone through carbon NMR and hydrogen NMR for spectroscopy. On the MCAT, my personal experience is I've only seen HNMR. So I would say study HNMR more than your carbon NMR. You might want to ask others as well what their experiences were, just to be on the safe side. NMR is used to determine the types of hydrogen families on a molecule to further elucidate molecular structure. NMR detects RF radiation from nuclear spin of the hydrogen atom absorbed by the nuclei. The hydrogen atom creates its own magnetic field, which interacts with stronger external magnetic field, which is that of the machine. The spins of the protons become aligned against. So if we're talking about the protons being aligned, that means that they're going to be against, and then against, which is anti-parallel, or with, which is parallel to the external magnetic field. So everything is in comparison to the magnetic field. These interactions ultimately give us our data to know the hydrogen families or neighboring hydrogen atoms on the molecule. You don't really need to know all that in detail. I just wanted to give you guys a background of how HNMR works. It's important for MCAT purposes. It's more important to understand how to read NMR data than to know exactly how the machine works, which is exactly what I just said. I was moving ahead of myself. So HNMR scales from 0 to 10 parts per million. The proton has shift values, which are measured against a standard, which is the tetramethylsilane. Since all 12 hydrogens, this is basically background on how they came up with that standard number. Since all 12 hydrogens in tetramethylsilane are equal, the brilliant science geniuses arbitrarily assigned TMS, which is the tetramethylsilane, as the standard value at or as 0 parts per million. So that's how we get that range from 0 to 10. All shift values are measured and referenced against it in the magnetic field of the machine, and that produces our data. So, reading our NMR and peaks, we have shift values, we have chemical shifts, and we have peak positions. All that means the same thing. So we go from high frequency, which is 10, to low frequency, which is 0. Energy absorbed is represented as a peak on the spectrum, and I'll show you more details of this in just a little bit. If you see a number next to a peak group, it represents the number of protons associated with each absorbed signal in the spectrum. If you have a value that is downfield, if you know, so you have downfield shift, and then you have upfield shift. Your downfield are going to be deshielded or unshielded. So the protons feel the external magnetic field more, and signals will appear farther downfield from the 0 parts per million. So I will draw that in just a second and show you what I mean by that. So the proton's environment, if you have a value more upfield, that means that your protons are more shielded. So the proton's environment feels the external magnetic field less. So the position will be closer to 0 parts per million. Okay. So here's a sample. On the y-axis, you will have the intensity absorption peak, which is the RF values. And then on the x-axis, you have the peak positions in parts per million, which range from 10 to 0. Peak positions tell you what functional group is present in the molecule of interest. And let's see. I will answer that question in just a second. I'm going to show you all this next slide. So this goes along with learning those key absorbances as well. Again, I wouldn't try to memorize them. I would just say, remember a few of them, and then go from there. I'll just leave it on here for a second while I read through questions. And then I'll move over to this slide. Okay, so we will use, to answer your question, we will use fluorine and carbon as an example. So because fluorine is more electronegative than carbon, it pulls valence electrons away from the carbon. And that decreases the electron density around the proton. Does that make sense? So deshielding is due to reduced electron density due to electronegative atoms. Yes, I can do that. Okay, thank you. I'm glad that made sense. Okay, I got one more question that I need to go back here for. Okay, so here's the purpose of NMR. It's the measure of the magnetic spin associated with the hydrogen nucleus. And it's used to determine the type of hydrogen families on a molecule, so that we can know exactly what the molecule looks like after we read the data. Hydrogen family means, let me go back to one of my molecules. This is a great question, actually. Okay, so let's take this for example. Let's look at number one. Right here, we have 3 hydrogens on the end of this carbon. That's a hydrogen family. It's just a group of hydrogens on the molecule. So here's a family, and here's a family. And same thing on this molecule. You have 3 hydrogens here at the end of this carbon, and you have 1 here, and you have 2 here. So this is a hydrogen family. That's a family of itself, and that's a family. And I got them all. Does that make sense? Yes, perfect. Thank you. I'm glad that is good to go. So let's go back over here. Okay, let's go ahead and think about this question. What H&MR feature can distinguish pentanol from 2-pentanone? So look on the left and think about look here on these and these and think about what pentanol has that 2-pentanone does not have, and vice versa. I would say memorize a few of those and have them down so that you're not trying to think of it on the spot as you go through the test. So I'll give you guys a second to think about that. And I want to go back over here and show you all something else while you're thinking about that question. So on our H&MR spec, we're going to see an H&MR spec will be, I'll use this one as an example. So this is a really bad drawing of an H&MR spec. Sorry. So H&MR is really supposed to tell you about, what protons are in the area of your molecule. And this is, like I said, a really bad drawing, but we will go over more in office hours if you need to. So that's what you would see if they gave you an H&R spec on the exam. Hopefully a little better drawing than that. Okay, someone said, which ones would I recommend learning? My advice would be learn the ones that you don't know. Meaning, if you know for sure alcohol, I think alcohol is always the easiest things to learn because it's so different from all the other molecules. Okay, let's keep moving so that we can get through all of them, and I'll come back to the questions very quickly. So to answer this question, what does pentanol have that 2-pentanone does not have? Pentanol has an aldehyde that 2-pentanone does not have. The aldehyde's hydrogen will show between the 9.0 and 9.8 parts per million range. And this is how you can distinguish two relatively similar molecules using HNMR. Someone asked which ones would I recommend memorizing. I would say the ones that are pretty tricky or common or too close together to really distinguish. So to not be able to distinguish. So the ones that are kind of similar, like this example, I would definitely say try to remember those. Sorry. No other hydrogens split the methyl group. So that's how we're able to distinguish these two from each other. The methyl group will show up as a singlet in HNMR. Any questions on that? Yes, I can do that. Splitting patterns of signals. So splitting is caused by non-equivalent neighboring protons, magnetic field interactions. So the machine works by measuring the external magnetic field with the proton's nuclear spin. So three of peaks from absorbance signals. The number of neighboring H's plus one. So that's the n plus one rule. There's definitely a typo in that sentence. So sorry about that. So the n plus one rule will help you understand the splitting patterns of the signals. There are no immediate neighbors. It's on the next slide, yes. So there are no immediate neighbors. Its absorbance signal is a single peak. So a single peak is a singlet. There are 6 important ones that I would say to try to know how to identify 6 different splitting peaks. So there's singlets, doublets, triplets, quartets, pentets, sextets, and multiplets. Yes. Are there any questions on that? And I have more on splitting in a few seconds. So we'll keep moving through. So the integral is the number of hydrogens that make up the signal. The splitting is derived from the coupling of hydrogen neighbors. So on a molecule, like we said before, we're looking for hydrogen neighbors, which will give us our splitting patterns. So I think it'll be better to go over that during office hours. That might be better. So we're basically trying to understand the neighboring hydrogens. So if we're looking at this hydrogen, these are what we are calling neighbors. Okay. If we're trying to evaluate the splitting pattern of this hydrogen specifically, then we're looking at those neighbors. Yeah, my office hours will be this Thursday. And I will have to send out the time for that. If you're thinking about the shift value, that is the location of the peaks determined by the hydrogen's local magnetic field's interaction with the stronger external magnetic field. So these are I wrote these for you guys as definitions in case you were lost or confused. If it's more than 3 away, then it's not considered a neighbor. So here is, I'll just let you guys have these to look at on the slide so we can continue moving through. We have a lot more to cover, and I don't want to go over the time. So if you have, I'll just do one example. If there's 0 hydrogens as a neighboring hydrogen, you'll do 0 plus 1, which will give you 1. That is going to be your splitting, signal splitting, and the shape would be a singlet. So you would only see 1 peak. Okay. And then I'll go ahead and review this. So the key to IR, UV, and HMR is to use as much data as possible to further elucidate the molecular structure. So we have to use all 3 of these together to really get a good idea of what our molecule is. And I already told you all that. CNMR is rarely used for structural elucidation because it would only give us an idea of how many unique carbons there are in a molecule. For these questions, you will have combined data, and you should try to average 60 seconds per question for your MCAT. I think it will be better to go over that at the end of class or during office hours, if that works for everyone. And then I guess I'll answer this question really quickly. So to find the NMR splitting pattern for any given molecule, you would count the number of identical hydrogen atoms that are adjacent to the atom of interest, and then add 1 to that number. Does that make sense? Okay, we will keep moving through. So we're gonna go over organic chemistry lab techniques. Okay. Organic chemistry lab techniques consist of separation, purification, and identification. And the key to these lab techniques is using states of matter, which are solids, liquids, and gases, to separate, purify, identify organic molecules. So for separation, there are a few different techniques we're going to go through, which is chromatography. We're going to go through the stationary and mobile phase of chromatography for each type of chromatography. There's TLC, thin layer chromatography. There's column chromatography, gas chromatography, and acid-base extraction. Okay. So for chromatography, a sample is introduced to a stationary phase using silica gel or a viscous oil. The sample will have properties that cause it to stick to the stationary phase. Stationary phased sample is introduced to a mobile phase, which is usually a liquid or a gas. The mobile phase will then move through the stationary phase. As it moves, it takes sample components with it from the stationary phase. This is called the elution. Each component from the mobile phase will move at a different rate depending on component's affinity for the stationary phase. And that is a key point. So the mobile phase will move faster if it has a lower affinity for the stationary phase within the column. So the idea of separation occurs as components move at those different rates. For thin layer chromatography, it is used to analyze what is in a sample. Stationary phase is the solid, again, the silica gel or alumina plate, which is very polar. The mobile phase is a liquid solvent mixture, which is called eluent of polar and nonpolar organic solvents. So, and then the steps are listed 1 through 5. A mixture of product or sample is combined in a glass beaker. A capillary tube is used to retrieve sample and spot the capillary action. A spot is placed onto the stationary phase or thin layer plate. The mobile phase is prepared in a separate sealable beaker. The stationary phase plate is placed into the mobile phase and sealed. Over time, the eluent rises above the capillary action and products successfully separate. There's a calculation for TLC, and that's called the RF value. So if you all see this white sheet right here, so in lab, you would have used your capillary tube to spot A, B, and C as it shows on the paper onto this white paper, which actually contains a chemical substance to allow the spot to move. The mobile phase is the solvent, and that's the blue, the bright blue down at the bottom. So that's actually inside of the beaker. So you're gonna dip this white piece of paper into the beaker, and then you would cover it up. But all that is done after you draw out the origin and then measure out the solvent front with your pencil, and you would mark that. The solvent front is where the solvent travel ends. And then you would use your ruler to measure the distance of substance A to the center of the point where it stops. Does that make sense? So the distance solvent is equal to the solvent front minus the solvent original point. To calculate the RF value, you would use the distance spot traveled and divide it by the distance solvent traveled. And you would actually have values here. You would have those numbers here. Okay, because you would measure these points with the ruler, and it would be an actual value to put into those. So for example, substance A, the RF value would be distance of substance A minus the distance of the solvent. And the distance of the solvent is measured here from this point to this point. So the greater the RF value, the more nonpolar the substance is. The smaller the RF value, the more polar the substance is. And then your RF values will lie between 0 and 1. The R value is the physical unitless constant associated with a solid, a solvent, or absorbent combination. Separations occur due to the relative affinity and polar or nonpolar properties. Do you all want to take a 5 or 10 minute break, or do you want to keep going? We'll wait for some answers here. Yeah, we could go ahead and take a 5 minute break, 5 to 7 minutes. Can everybody hear me okay? Okay. How about now? Is that better? Okay. All right. Let's see here. Okay. Is there still an echo or are we good? We're good, good. Okay. So in office hours, I know some of you have a lot more questions about splitting and you may have questions regarding the lab techniques. So we will cover graphs and things like that in office hours. And then next time I will make sure to add all those things into these slides. So I really appreciate everyone's feedback on that. My office hours will be every Thursday. Let me make sure I give you the right time. Every Thursday starting this Thursday from 5 to 6 Pacific time. So I won't be available for office hours on December 2nd. That's the only Thursday I won't be available. And then if it goes over an hour, then that's fine too. So Thursday from 5 to 6 Pacific time. Okay. So we were on chromatography, and so we'll go into column chromatography. Let's see. So column chromatography is a large scale 3D version of the TLC. Column, here are the steps. The column is filled with the stationary phase, which is silica gel or cellulose or alumina. The bottom of the column is usually packed with glass wool. The column is prepared and packed by using a slurred stationary phase in which both stationary and mobile phase exist. Within that is the sample. So the sample is loaded at the top of the column. The mobile phase should be loaded and will continuously be loaded until separation is complete. Gravity is key to this version of the TLC, to column chromatography. So gravity pulls the mobile phase and the sample down the column. The seventh step is the interactions occur with the mobile phase that cause the sample to exhibit affinity for it or to it. Separation occurs and fractions of the sample are collected one at a time to ensure separation. So a few things to note about this technique is the molecules that move the quickest down the column are the molecules in the sample that interacts with the mobile phase the least. So the key is to differentiate between how the molecules are interacting with the stationary phase and how the molecules are not reacting, how the molecules are interacting with the mobile phase and the stationary phase. So the molecules that move the slowest down the column are the molecules in the sample that interact with the stationary phase the most. Okay, and those two things are the key things to remember for the MCAT, because you're going to get a lot of questions with as far as interactions go. And the key to each technique is to know the affinity, like molecules affinity. So Column chromatography, again, is a 3D scale version of the TLC. So elution time is measured as T sub elution, which is equal to the amount of time it takes for the component to elute from the column. This value is reported as fractions. Stationary phases will determine the type of chromatography technique being used. So depending on your stationary phase, you will determine what type of chromatography you should probably use in the lab. So I'm sure you guys heard of ion exchange columns, affinity chromatography, absorption chromatography, and gel chromatography. So these aren't, I would say to look into this one more for the MCAT. Ion exchange column is pretty common. And I would also say look into the ligand. So ion exchange and ligand, I would say those two. All right. So GC chromatography is gas chromatography. During this process, a sample of a compound is vaporized into a gas. The vapor is forced through a packed column using elevated pressure from a cylinder of an inert gas. The machine measures retention time on the column by recording collisions of the gas molecules as molecules leave the coiled column and hit the detector. These collisions are converted into peaks on a graph, which can be integrated to determine relative abundance. And your relative abundance is going to be your key for your data from your GC. This GC chromatography is actually large scale, so you'll see these in industrial sized machines. A few notes for this one is the stationary phase is usually a viscous silicone. The mobile phase is a gas. And you guys know the difference between stationary and mobile, right? No one assume. I know I've been moving quickly. Yes, okay, good. So the mobile phase for GC is usually helium, argon, or nitrogen, and flows at variable rates because those gases have variable masses. So, and at variable pressures as well. So gases move differently based on pressure and mass. So this technique is best used if for small samples. Your samples should be highly volatile at 200 degrees Celsius and inert compared to the stationary phase. More than one sample can be analyzed simultaneously via GC because, again, as I mentioned earlier, this is usually on a large scale industrial size machine. The greater the area means the greater relative abundance and more material present. And here is the apparatus setup for a GC. So this is in your Berkeley review book. So you'll have this, and we'll just read the bottom of figure 4.7. The carrier gas is added at this point, which here it says usually helium, so it's usually added there. The positive gauge pressure of helium gas at this point forces the vaporized sample through the packed column, which is here, and into the detector, which is here. The detector reads collisions of the gas particles moving through it, and collisions, the chart, usually these machines are connected to a computer to print out a chart afterwards, which is your data. The chart graphs intensity of collisions versus time. This means that no identification can be obtained directly from gas chromatography. The retention time depends on the nature of the column and the structure of the compound. And we'll go into more details on that if everyone has questions during office hours. So for acid-base extraction, the solubility differences is key. So here are the steps for acid-base extraction. You'll have 2 or more immiscible solvents that are combined. Immiscible solvents are most common for this technique, but there have been scientists who use other solvents. But this one is the best to use for better results. Compounds are separated based on their pKa values. I'm sure, I think you guys had Todd maybe go over pKa values. Maybe. So compounds are separated based on their pKa values with acid-base extraction technique. Yeah, we can do that. Just 1 second, I got 2 questions here that I want to answer. Okay. All right. So I'll give an example of immiscible solvents. So an example would be when you mix oil and water together. They don't come together completely to form a homogeneous solution. So immiscible means they don't completely mix together. So in acid-base extraction, you're going to have a solution that maybe that's one solution, and then you might have something like sit on top or bubbles that come up to try to go into this phase. I mean, into that layer. Are you asking to go through pKa values briefly? A little bit more to get through, but I think we'll be able to do it. Okay, sorry, I'm reading through questions right now so I don't miss anybody. Okay. Okay, so briefly, I'll touch on pKa values. So, and if we have to, we'll go over them some more during office hours. I'm just gonna write notes about what we should cover during office hours, if you guys would like. So far I have splitting patterns, graphing for each type of technique that we've gone through here. Graphs of UV, IR, and spec. And is there anything else that I need to note? You guys let me know and I'll write it down so we can be prepared for Thursday. So I know this is a lot of information, but on the MCAT, a lot of things, you're gonna notice a lot of things are gonna be combined. So the idea of acid and bases might be combined with the idea of like, let's see, what's a good example? New example. So you might get an NMR question with an IR question combined. So a lot of the topics that you guys are going over during these lectures are gonna definitely come together as one question. So you gotta be able to go back and forth between topics and ideas. So that will be good to practice when you're going through your practice questions, your Berkeley Review practice questions. Oh no, no worries. I like questions. I just want to be able to answer them the best way for you guys to understand them, because I know it's a lot of information. You guys are reviewing 4 years of work in 2 hours, so it's definitely hectic. I know that for sure. So questions are good. I just want to make sure that I get everybody's questions and that I can explain it in the best way possible. So here, let's go back to acid-base extraction and then briefly hit on the pKa values. So the smaller the value of the pKa, the stronger the acid. Okay, let's just put that as a note. So the smaller, oh, that's not working. My screen's not big enough to do that fancy stuff. Smaller pKa equals stronger acid. Okay. And then your pKa will be, it doesn't have a unit on it, so it'll be a single number without exponents. Okay. Let me see if I'm missing anybody else's questions, and then we'll keep moving forward. Okay. I think that's the best, most briefest way to go over pKa values. As far as the actual numbers, we can try to do that during office hours if it's okay with you guys. Okay, so here are the steps for acid-base extraction. So 2 or more solvents that do not completely mix together, which is immiscible, are combined into one beaker container. And then compounds are separated based on their pKa values. So if you have a stronger acid, it's going to separate from a weaker acid or a stronger base with a biphasic solvent mixture. So this is a heterogeneous system. Protonation and deprotonation occurs. So you remember in lab where you mix 2 solvents together and then you were supposed to shake it up, and then you're supposed to put it back and wait a few seconds. And then that allowed the separation to occur. And then you shook it up again, and then it separated again. So we were knocking out protons from one layer to the other, because every time you mixed it, these 2 would come up and they would separate. This is a very terrible example, but I promise we will do better on Thursday in office hours as far as photos and pictures go for separations. Okay, so basically when you shake this solution, the protons go from one layer to another and separate. Does that make sense? Let's keep going, and then I'll ask that question again and see if it makes more sense, because I think if we keep going, we can get this. So the main key for acid-base extraction is the solubility differences. So in step 2, compounds are separated based on their pKa values with a biphasic solvent mixture, which means a heterogeneous system. Protonation and deprotonation are occurring as you shake the solution. This causes an increase in the compound's water solubility of an ion if an ion is generated. So a loss of charge results in an increase in preference for the organic layer, while a gain in charge results in an increase in preference for the aqueous layer. This is how the solvent layers are extracted out of solution. So in lab, I'm only pointing out this key point right here. There's more steps before you get to this shaking part, but the shaking part is really what causes the organic layer and the aqueous layer to separate. Does that make sense? And this is the point of acid-base extraction, is when you shake the solutions, they separate based on if an ion is extracted out of the solution. For example, if there's an ion in the organic layer that's more soluble in the aqueous layer, that will go over into the aqueous layer as the shaking occurs, and then you separate it. That causes the separation. So in step 4, acids that are not water soluble will precipitate out and vice versa. So that's how the layers separate. Okay. Does that make sense? Yeah, that's a really terrible drawing. Okay, let's keep going. So now we're going to move on to purification techniques. Purification techniques, we're going to go over distillation and recrystallization. So distillation is usually used for liquids. We have simple distillation, which is simple, and then we have fractional distillation, which is a little more complicated. For recrystallization is usually only used for purifying solids. So purification techniques and this is specifically simple distillation. So the key to simple distillation is used when there is a change in boiling point. The change in boiling point is a large change. So the difference in boiling point is large. So it has to be at least 100 degrees Celsius different. Okay, so in a flask, you'll have liquid A, B, a mixture of liquid A plus liquid B. Anything under? Yes, you'll have a smaller difference in boiling point for fractional distillation. So for simple distillation, the first step would be liquid AB is boiled, producing the vapor of the lower boiling point liquid. So the vapor that comes after, let me write some heat in here. So this is the hot plate. So the liquid AB is boiled, which produces vapor or gas of liquid A, of the lower boiling point liquid, whichever it is, liquid A or liquid B. The vapor that escapes is the lower boiling point liquid within the liquid AB mixture. Does that make sense? The vapor is collected into the condensing column in the gas phase. So the vapor is collected into the condensing column in the gas phase, and the vapor condenses until it returns to the liquid phase, at which point it is collected using a collection beaker. And I have an example of this that follows, so we'll go on to that. The apparatus setup. So here we have the liquid phase. We have our hot plate, which is boiling liquid AB, your thermometer, is here, so you can measure and not go over that certain degree, so you can make sure that your vapors properly separate out. Here you have your gas phase. This part is the gas phase, meaning your lower boiling point liquid vapor comes up, enters into the gas phase, and then it is condensed by the condensing column. And then it will go into the new flask, which is going to be the pure phase liquid. So the key to this is the lower boiling point liquid here is going to be the first to create a vapor, to be recondensed and redistributed as liquid in the new flask. And that's how your separation occurs. Purification of this occurs. Does that make sense? All right. Any questions on that? Any other questions? I think that one made sense to everyone. Okay. So a few more things about simple distillation. As long as the thermometer does not read higher than the highest boiling point's liquid. Okay, let me reread that. As long as the thermometer here on the apparatus does not read higher than the highest boiling point, liquid's boiling point, which was liquid A, you will know that your receiving flask, which is this one, is full of the lower temperature liquid. So you have to monitor your temperature gauge as you go through this process. So it would be nice to know what your boiling point is for each liquid before you start, so that you can monitor and make sure that you're only getting the purest form of whichever comes through the receiving flask. The heat plate will be set a few degrees higher than the lowest boiling point, and the condenser will provide a decrease in temperature to accommodate the evaporated gas phase. Lower boiling point gas phased liquid. The higher temperature lower point gas phase liquid. This causes the gas to reform into liquid phase, as I explained in this crazy picture that I made for you all. Does that make sense? Okay, good. So, key components of simple distillation one more time. Your distillation flask holds the volatile liquids AB. So this is your mixture. I'm going to use a different color. This is your mixture. You have your three-way adapter here. 1, 2, 3. And then your heat source, your hot plate, that heats liquid A and B, your temperature thermometer to measure to make sure you don't go over the volatile, the evaporated gases temperature, the liquid's temperature. Then you have your condenser here, your collection flask here for the pure liquid only. And then you have a vacuum flask, just right here. Okay. So let's talk about fractional distillation. Fractional distillation is used to separate liquids whose boiling points are closer together. So someone said in the chat, is it closer than less than 100 degrees Celsius? And that was correct. So the difference is less than 100 degrees Celsius. The closer to a 30-degree difference is best for fractional distillation. Okay, just 1 second. Which one was? I'll go back here for just a second so someone can see the diagram. Okay. That is where the vacuum flask would be, basically to make sure nothing escapes before it reaches. Okay, great. Thank you. Okay, so for fractional distillation, you're going to have a fractionating column that is used. It's similar to simple distillation. The key is to redistill the distillate to retrieve a higher purity. And the fractionating column does this well for us. Advantages over simple distillation is you'll have higher purity and more constant vapor pressure, which reduces solution bumping. So fractional distillation is a little better if you want to get a higher purity, and we'll go into that shortly. The disadvantages is that it's a longer process than simple distillation. So the thing to keep in mind is simple distillation and fractional distillation is very, very similar in technique. A fractional distillation is just doing simple distillation over and over again for higher purity. And then there's going to be a graph that I'll show you for that. Inside the fractionating column, the temperature drops and the lower boiling point liquid vapor condenses back into liquid phase along the walls of the column. And I'll show you how that works in just a second. The liquid phased substance revaporizes, resembling a second distillation process. The second revaporization is the more purified version of the starting substance. So you see what I mean by you're going to be doing simple distillation over and over again for fractional distillation. The higher, less volatile boiling point liquid will reflux back into the boiling flask. So that means it'll basically just drop back down into the boiling flask, while the lower boiling point liquid vapor travels onto the collection flask because it is more volatile. The more condensation evaporations that occur within the fractionating column, the higher the purity you will get. So the key is to redistill the distillate to retrieve a higher purity. So this is a sample taken along the column of a fractionating column. So this is a close-up of a fractionating column. Samples taken along the column will reveal that the most purified vapor of the lower boiling point liquid will be closer to the top of the fractionating column. So the light purple is what we're focusing on. So in this example, your first distillation round here will give you an 80% purity. If you took a sample from here, you would have 80% purity for liquid B. because we want the lower boiling point liquid. Your second distillation will be a 97%. And then your third will be closer to 100%. So the key with fractional distillation is that fractionating column will help you get a more purified version of your liquid. So it's just simple distillation over and over again. Any questions on that? Okay. Looks like there aren't any questions for that part, so we'll keep going. So vacuum distillation is used to purify high boiling point liquids, which require boiling points above 150 degrees Celsius. The vacuum distillation will be the same as the simple distillation process, except a vacuum is added on the apparatus at the point after the condensed liquid has been collected. The vacuum reduces the pressure in the apparatus, which reduces the boiling point of the liquid, which increases the liquid's vapor pressure. So the purpose of vacuum distillation is that it prevents heat-induced decomposition. So you'll get more substance yield. Does that make sense? And I know we don't have photos or graphs on these, which is why I said I'll definitely provide some of those during office hours. And next time I'll definitely add them into the lecture. I think that would be much better for you guys. Recrystallization, which is also known as selective precipitation. And this is used to purify solids. So first step is an impure solid is added to crystallization solvent. The solid is dissolved into hot solvent. The second step is the heat will help filter out any insoluble solid impurities. The key here is to do this next step slowly. Slowly cool the solution to precipitate the purified crystals. Doing step 3 too quickly may cause your pure product to redissolve into solution, and you'll have a lower yield. I don't know if you all remember, but in lab, maybe your teachers really emphasized the slow part for step 3. Cooling causes the product to precipitate out of solution as crystals free of impurities. Yep, exactly. Exactly. That is correct. So for recrystallization, your solvent choice is essential. So you want to choose an insoluble at low temperature. That's the key for that part. Solvent to avoid reflux. And reflux is what someone said in the chat is having your pure go back into impure in the lattice structure. So you want to choose an insoluble at low temperature solvent to avoid reflux. And reflux occurs when the solvent boils but condenses on the flask walls and drips back into solution. So that's counterproductive to your recrystallization process. So next, we're going to talk about identification. Your physical properties include your melting points and boiling points used to identify molecular compounds. So this is, I'm not sure if you guys remember your melting point tests and your boiling point tests. You retrieved a sample in a capillary tube and you put it into the machine looks like a little microscope, but it's also a heat source. So you look into the microscope as your sample and you time when your sample melts, and then that is your melting point test. Okay. For your chemical tests, you should choose reagents that will react with a minimal number of functional groups. So you should be able to identify functional groups that are present in a molecule using chemical tests. Positive tests are indicated by color or phase change. Your test agent must be the limiting reagent in the reaction to limit excess interference. Next is derivative compounds are normally ID'd using using melting point. Sorry, misspoke. Okay. And I think that is everything. Do you all have any questions that I can try to answer right now? I know that was a lot of text. So like I said before, I will definitely make sure to add those graphs and we can talk about splitting pKa. We can talk about those chemical tests during office hours as well. Is there anybody else that have any questions that they want me to prepare for during the office hours from this lecture? Yeah, it is good when it's just review, so. Okay. Anybody else have any questions? You're very welcome. Yeah, that's fine. I'll look at the emails and prepare the answers for you, and I can either send them to you or we can cover it during office hours. You're welcome.